Hi, everyone. Today, we're going to share our findings on comparative study on deep learning models for environmental sound classification. And this is actually our second time to do this after our first comparison 5 years ago. If you're interested, we included a link at the end of the slides for our first comparison. So as we all know, audio tagging is a task that has been widely deployed onto smart speakers and cameras. Uh, and the largest existent data set for audio tagging is the audio set, which contains 2 million samples. They're all 10 seconds long, weekly labeled sounds of 527 different classes. It has a balanced training set of about 22K and 2 million unbalanced training set. And the evaluation has about 20,000 samples. So just to take a glimpse on the task of audio tagging, essentially we're learning the features from all these different acoustic classes. And then from the log-mile spectrum, we can see that they are drastically different from each other. But also the challenge here is usually the data quality is not very high. They're weakly labeled and they contains a lot of variation. So let's start with a few specific questions we want to ask ourselves with the paradigm shift from recurrent modules to recent, more popular transformer models. So is a transformer family actually better or worse than the convolutional families? So yeah, let's dive in and then put all the models in a fair comparison and see how they do. So here, the model in comparison are, there are 6 models in comparison. We compare from left to right convolutional transformer models and the vanilla transformer models as well, and the convolutional recurrent networks and the new architecture, which is the vision transformer, only started from last year. And we also compare conformer and the ResNet architecture as a baseline. So this graph might be very daunting and overwhelming to look at. Let's break it down from left to right. So you can see the conv family has pounds, ResNet, PSLA, ERA, and then S. And then the attention family has conformer, AST, Passat. So we don't separately list Passat here is because it's very similar to AST VIT architecture. Both of them actually use the pre-trained VIT weights to start from to warm start their model. Now we're going to break down all these different recipes and different systems to details. So according to their data, according to optimization process, and then their training data set. So there are a few specific questions. The most poignant one is pre-training actually necessary, and what are the most important factor in improving those models, right? So in our finding, we find pre-training is not actually always necessary, and the learning rate seems to be the most important factor, and then kind of a whole act with a batch size. So we need to pay special attention to learning rates, and then tricks like gradient accumulation or momentum actually might not help the model training all the time. So let's first delve into pre-training. The intuition of pre-training was clearly elaborated in a paper in 2019 written by the inventor of ResNet, where he compared a pre-trained model on ImageNet and then tested it on the COCO dataset. So what he found out is basically we do not always need to, the randomly initialized model could eventually catch up to the pre-trained model in terms of performance with a proper fine-tuning. This is consistent with our finding as well, as we can see in our table, right? So the models without pre-training eventually catch up to the pre-trained model on with ImageNet. But what is astonishing is that because we don't necessarily have in academia, we do not have a larger corpus rather than audio set to pre-train. So the best we can do is pre-train from ImageNet, but that still works very well, even though audio audio log mail spectrums are very different from the features that we learn from the ImageNet pretrain, which is essentially the edge or the tiny feature, the tiny little boundary features from the image. So it still helps. The only self-supervised baseline we're listing here from last year from the Facebook group seems not that successful compared to all the other baselines that we're listing here. So let's dive more into the optimization tricks. This is where our guideline, we found our intuitions. We found out learning rate decays beat constant learning rate by average 2-point mean average precision. So there's a strong intuition behind that. And then the governing rule is basically learning rate is linearly correlated with batch size. We need to tune them to be linear rate. So there was a paper in 2018 written by Sam Smith, and then he talks about don't decay learning rate, but increase batch size. So this intuition actually turned out to be very helpful in our optimization. Basically, the caveat is to fill up the GPU towards the full capacity with a large enough batch size, and then amplify the learning rate accordingly. This will not diminish the training accuracy, but also in the meantime speed up the training process by a lot. And we also found that bad learning rate will cause some models, especially the transformer models, to be stuck in very specific minimas and then just cause the entire training to fail. Basically, our suspicion is here, as we can see from the graph on the right. There is a paper talk about that transformer architectures tend to have a more tend to have sharper minimas, where it's basically harder for the optimization to get to. So if the learning rate is too large or too small, it's there's a good chance that we could believe it missed the best point. Following this intuition, so we want to slow down. Actually, instead of speeding up, we want to let the model tread carefully towards the minima, right? So the intuition behind that is basically in order to adapt to the sharp minima, the model needs to be slow or just have the enough speed to learn to discover where is the minima, so that in that case, gradient accumulation in our experiment also doesn't seem to help. So if we accumulate too many gradients, it's moving too fast. And then the trick of reducing the beta 1 from 0.9 to 0.95 is actually reducing the speed of atom by twice. This actually helps with the final performance. And we also found that weight decay, the regularization does not help in this case necessarily, because AudioSet is actually large enough, so the model is not very prone to overfit. So let's talk about the issues in the data itself. AudioSet itself is not exactly like ImageNet, because AudioSet labels, their labels contains ontology, and the quality of the labels are quite different from class to class. So there are good classes, there are badly labeled class. Sometimes, there are only 20% of the labeled event actually exist in certain classes. So as we can see from figure 2 here, the contrast is drastic. So take a CRN model, for example. If we use the entire AudioSet test set as a benchmark versus use only the 90% quality quantile as a benchmark, that resulting difference is almost a 10-point MAP, which is significant. So that is basically telling us that if someone reports AudioSet with a smaller test set, there's a higher chance that that actually benefit from a smaller test set, because there's a good possibility that it can boost up a few more digits without even tuning the models. There's from what we observed, there is about 5% difference across previously published work in terms of the size of an audio set alone. That will cause huge variations. And in our experiment, we compare mainly two features, which is one is the 128 log mel filters. The other is with only 64 mel filter, and they only differ by about 2 MAP. So in terms of in the cases of where we actually want an efficient system with less computational requirement, we actually need to advocate for usage of smaller features. So given all that intuitions, we have our own implementation of all these six different models with a drastically different parameter size. But interestingly, we can observe here, right? So without pre-training, convolutional transformer architectures, the eventual performance of these well-trained models can eventually catch up with the AST VIT equivalents, where the VIT models do rely on pre-training a lot, and their eventual performance will not be too good if there was no pre-training. And then convolutional recurrent network still stays to be very competitive. The performance gap between that and the VIT models are not very huge. So these are all rather astonishing sort of counterintuitive findings that we observed in our experiment. You can see more details in our open source code repository. So we want to understand a little bit more about VIT and so-called audio spectrum transformers. So we did a case study on their number of patches by tuning the frequency stride and then temporal stride. And then as we can see, the number of patches grows quadratically with the F stride and T stride parameters, and it reaches a sweet spot of beyond 500 patches. Then all the performances are quite similar. And then from here, we can see the smaller features with enough patches still perform quite favorably. And the large patches feature would cause too much of a GPU drain. So when we use large features with a very small striding, then it will result in an explode of a GPU memory in this case. And the side question and probably helpful question is that how much does data augmentation help in our case? And then this is our finding. Basically, across the board, different type of data balancing tricks contribute to about 0.5 to 2 point of a performance gain in all the data balancing. And note here that our system also adopt the same intuition as AST to normalize all the weights to 0.5 distribution instead of 0.1 distribution. This is apparently to be more suitable to the pre-trained VIT weights in the TIM library. So here's our finding in summary. So basically, we found out that in a lot of cases, if we do not have strict requirement on performance, we should use smaller features. And pre-training is not always necessarily better than train from scratch or randomize the weights. And modern training recipes like learning rate decays and all the other tricks are very helpful to boost up performance. And the hybrid models with both global and local information aware tend to have the best efficiency, kind of a strike balance between efficiency and performance. And attention models, they necessarily have a lot more parameters and more sensitive to train, and they tend to have a sharper loss landscape. So these are kind of a recap of our findings. You can find more details in our open source repository and read our paper for more detail. Thank you.